right, thanks for joining, everyone. Welcome to Ops 211, Continuous Integration and Delivery into Kubernetes. My name is Justin Brooks. I'm the Director of Engineering at SADA Systems. I've been working there, just some background, I've been working there about 8 years. I've been the Director of Engineering for 4. SADA is a reseller for Google Cloud Platform. We help customers onboard onto GCP or transform their existing GCP applications into more optimal implementations. In this presentation, I'm going to be going over a little bit about Kubernetes, a little bit about CI/CD, and our best practice recommendations for what we implemented for one of our applications for one of our products called Atom. Okay, so what is continuous integration? You guys probably already have a brief understanding of what that is, but just to rehash it, it involves developers integrating code as often as possible within a shared repository, and the process around that, including automating building and testing for that application. It allows teams to get feedback quickly and find issues early, and that it can be extended further after you've implemented CI into either something called continuous delivery or continuous deployment, where those changes are automatically deployed into various environment levels. So on the screen here now, we have a sample application infrastructure on what something could look like that incorporates Kubernetes. You'll notice that the important components here are the implementation of the container registry for hosting Docker images and GitHub for your source control. All right, so briefly about Kubernetes. So at a glance, this is sort of the representation of the architecture of Kubernetes. It helps you manage container clusters, supports multi-cloud, bare metal environments, and supports multiple container runtimes. There are several also additional benefits you get out of running GKE on Google Cloud, including auto-scaling and auto-healing. One of the components of Kubernetes is the API server. So this is basically how you do all of your interactions with the Kubernetes cluster, and is essentially how the CI tool is going to interface with the cluster as well. It's an API. It's all API centric. There's no private APIs. There's no system-only call. Everything communicates through the API, and it's a RESTful type of service. So you see, we have an example of that. You can actually see on the bottom right-hand side, although you can't really read it, the detailed logs that you get in Stackdriver showing all the API calls that are being made as part of a deployment. Controllers are fundamental to how Kubernetes work. It's a piece of code that watches a Kubernetes API and reacts accordingly. Essentially, it's code that runs in a loop, listens to the API server, and responds to changes. For example, when you want to create a pod, what you really want is to schedule something in the system. Scheduler wakes up in the system, determines where it's going to put in the pod, and it writes back to the API server. The kubelet then wakes up and orchestrates what you want to the system. So it's all unified together as part of this process that's part of the CI/CD pipeline. So the nodes are the actual worker machines that run the containers, manage the master components, including services like the container runtime, the kubelet, and the kube proxy. If you're running an on-prem environment, this would be a physical machine. If you're running in the cloud, it's most likely going to be a virtual machine. The container runtime has a interface which actually facilitates pluggability, supporting different types of containers, including Docker, RKT, and others. The kubelet is the most prominent controller, which implements the pod and the node APIs to drive the container execution layer. And the kube proxy is a service abstraction that groups pods under a common access policy. It programs the IP table rules to trap access to service virtual IPs and redirect them to the appropriate backend. Okay. The pods are small groups of containers and volumes. They're tightly coupled. They live and die together as they're spun up and spun down. And they have shared networking and lifecycle. The containers within a pod share an IP address, and they find each other via localhost. Now, a pod typically is set up to run just a single container, but it can run multiple if necessary, depending on the use case. Deployments are the declarative updates for the pod. So basically, you specify a desired state. The deployment controller then handles the actual execution of reaching that state. Services are an abstraction that defines the logical set of pods and the policy by which they are accessed. Each pod has an IP. Services provide a stable virtual IP so that even as you scale up and down, as part of your process for auto-scaling or any issues with self-healing. It maintains a single virtual IP that you can use to access those services. And finally, secrets and config maps. These hold all the sensitive information, such as passwords, OAuth tokens, et cetera. This is obviously going to be a key component of the CI/CD process for maintaining the secrets that are going to be distributed across each environment. There are numerous automatic secrets that are created by Kubernetes to store the credentials to access the API. They're base 64 encoded, not encrypted. The config maps are then used to store the non-sensitive information, and then you have an image pull secrets that you utilize to set container registry credentials. That's going to be crucial when we talk about the implementation of the CI/CD pipeline and how it interfaces. All right, Kube Control is obviously the main CLI that you're going to utilize to execute any actions against the cluster, listing pods, applying changes, things of that nature. This is another key component that's going to be utilized by our CI tool as part of the build and for the CI/CD component for the deployment. All right. So now we get into orchestration tools. These are key components of the CI/CD process that are utilized in the actual automation pipeline. So GCP service accounts are going to be crucial. Everything needs to run, should be running through a service account rather than a user account. You'll be managing those directly, typically either within some form of a deployment management solution or in the console or even via the gCloud CLI. Deployment Manager is a solution that's typically used, Google native, around automating the cloud deployment. So that you have your infrastructure codified, it's repeatable, declarative. The templates can also be pulled once, created manually for resource recreation, so you can reuse that across multiple different services. Now, Terraform is often a common alternative to this that's also useful. They both have their drawbacks. In this particular instance, we're talking about a GCP Deployment Manager implementation. All right, for automation, we are utilizing Travis CI. It's basically a hosted CI tool for handling all of the automation. All of our scripts are in there, so it handles everything from downloading the gCloud SDK, setting the appropriate zone, cluster, and project to deploy to, activating a service account, and installing the Kube Control CLI. Obviously, Circle CI is another alternative, Cloud Build, Jenkins, any tool. We actually use a combination of both Travis and Circle in our implementation. For our artifact repository, we're utilizing Artifactory. It's a universal artifact repository. It's been around for a while. It supports many software packages created in any language, CI/CD integration with nearly every provider, and hook properties for simple querying when you need to access specific items. It handles all of these different multiple repository types in Docker, NPM, Maven, Gradle, Debian, and generic repository. So those are key. Those listed out are key because those are actually the big components as part of our Kubernetes CI/CD deployment. The generic artifact repository in this case is utilized for the Android APK. That allows us to build and test and publish internally prior to releasing to the App Store. In this implementation, also note, in this implementation, we discussed potentially utilizing Helm. In our implementation, we do not yet use that, but it is a recommended use case and would be useful in the future to be hosted in Artifactory. Okay, so the build pipeline. All right, so this is where we talk about essentially how it's all orchestrated. So the application code, in our particular build pipeline, the application code is decoupled from the infrastructure code in separate repositories. So we have 2 different repositories for each service that we're deploying. The deployments are orchestrated on these various environments or specific containers are completely disassociated from the application code. So the process at a really high level, and we'll walk through that deeper later, is that the application code is built, compiled, and packaged. Code is pushed to the binary repository, which houses binaries of all sorts, including the NPM modules, any jars, Docker images, and any other binaries that might be needed. And then upon deployment, the binary is pulled from the repository and consumed as part of another build orchestration step or deployed to the appropriate resource. It's fairly modular and flexible. Note that we can actually build and orchestrate deployments across individual services or across the environment holistically. I'll walk through that in a bit. Okay, so part of how Artifactory is used on GCP. So we push images from the build. Obviously, during the build step, we create a Docker image. That's pushed to Artifactory. It can also be pushed to GCR. That's Google Container Repository. Note that that GCR implementation is a really good choice because there's native support within GKE. In the case where you're using a private repository, such as we are in this instance, we need to create an image pulled secrets link with a secret config type using that Kubernetes IO Docker config JSON. Okay, next we update the container image through the pipeline. So as I stated, you're essentially seeing on the right there an image of the source config for the infrastructure configuration, again in the independent repository. So we've gone through now, we've created the image, it's been tested and validated and successful. We update the Docker image tag in that config. Finally, we apply the changes to the cluster. Just one quick note, all of these items are actually automated through build scripts. I'll show you a little bit what that looks like when I get to the demo section, but none of this is actually done by hand. Okay, now we actually have an overview of this sort of cohesive, automated test, publish, and deploy pipeline. So starting from the top left, all of our code is hosted in GitHub or whatever repository you might utilize. It works the same way. That then, based on a pull request, will lead towards a build on Travis, which then pulls the code, builds the containers, any associated artifacts that are necessary, runs the test on a test environment, and publishes those artifacts to a binary repository, in this case, Artifactory. Those containers are then on the bottom, as you can see on the bottom right, they're labeled with the appropriate version numbers. This implementation, we have a microservices approach. So we have several different services that are tagged with all of the different versions for the multiple different services with their own version tags, their own environment labels, and as well as describing the type of code that we're utilizing for that implementation. Then Travis then makes a call to deploy this to the Kubernetes environment, which pulls the containers from that repository. Note also a key thing here is that monitoring is built in throughout the entire process through a number of different sources. So we are monitoring obviously via Stackdriver. We are also getting notifications from GitHub as those pull requests are being approved and succeeding or failing. Similarly on the Travis side, and all of those have hooks in our environment are integrated to notify us via Slack channel. All of that then creates our full application. So you see, this is utilized across all of our different environments for web, backend, iOS, and Android. And so this is a representation now of basically our completed infrastructure that I talked about we would be implementing. So you see it utilizes the shared services across the multiple clients, pointing to, through code, a load balancer to Kubernetes Engine. In this instance, we're not technically going to go into detail that here, but we have two database types for representing different types of data. We also have cloud storage, and the key factor again here is at the bottom, we have the representation of the binary repository being Artifactory and our source control being GitHub. Okay, so the continuous integration dev pipeline. So in this this is essentially how we get our code through to the integration steps all the way to our deployed in our dev environment. I'll walk you through that. So essentially we have our source code. In this case, I'm going to follow the source code path for our front end application. So our application source code is in our master branch. For that to work, then we have a pull request that's created, it's reviewed by our team, it's approved. Code is then merged into master with a new application version. That new commit triggers a build on the master branch in Travis CI. Then we see Travis CI making the call to now successfully build a new image, pushing it into Artifactory. Once that checks out, we move on to the next stage where it checks out the dev branch in the associated pod repository. So in this case, the pod repository is that independent infrastructure repository we're using separately from our application source code. And then it updates a deployment container image. The changes to the deployment YAML configuration are then committed to the pod repository in the dev branch. Then you see down there we have the web pod repository, the dev branch. It's then been updated. That commit triggers a new build process, next step in the build process, which builds the dev branch in Travis CI. That process is actually the deployment step. So utilizing a combination of gcloud and the service accounts we mentioned earlier, as well as several different build scripts that are part of the setup of that pod, it successfully deploys the resource configurations to the Kubernetes resource. Once that's done, the image on the Kubernetes side, the images will then be pulled into that deployment, and rolling updates are made to the underlying infrastructure. Oops. All right, so next step is the continuous integration for a single or multiple container promotion. So this would be if we want to just update. Again, I'm talking in this instance about a microservices-based environment. So if we wanted to just update a single service, we would follow this step. So here you see we have the backend pod. We have the backend pod for the dev branch. In order to promote to QA in this instance, a pull request gets opened against the QA branch. That pull request, once approved, then updates a single or multiple image tags, and depending on the configuration we're choosing, in the deployment YAML to the versions in dev. Then it's reviewed and approved, and then code is merged into the QA branch. Once that happens, that triggers a new commit on that triggers a new build on Travis CI. Again, running through a similar process to go through and actually execute the build stages and then deploy to the cloud environment. Okay. So this gives you a better sort of a representation of how the releases can be attributed from one environment to the next. So we have multiple different versions of each service in dev, UAT, and prod. We have an overarching version for the environment level that's noted at the bottom. In this instance, the front end and back end are different pods altogether. These pods have a series of containers that describe the pod. So going from one environment to the next involves kicking off a CI build process that reaches out to the deployment YAML for that specific environment and applies it on the appropriate cluster. This can be orchestrated with either different branches or different folders. In this particular instance, we're using the branch segregation for different environments. All right, so this is the in-depth process around how we do the continuous integration for environment-to-environment promotion. So when we want to take all of these services from one environment to the next, being promoted from, in this instance, QA to UAT, this is that workflow. So it starts off with, in order for this workflow to work, we have a separate environments repository that stores the status of each particular environment, again, using that branch segregation methodology. So it has a JSON schema representing each pod, and as well as the underlying containers of that pod. That represents the current version of that pod in that environment. So this environments repository, we look at it at the UAT branch. Again, similar process as before. A pull request is created from QA to UAT. That pull request is then approved. Code is merged into UAT with the versions from QA. And then once that happens, that new commit triggers a build on the UAT branch in Travis CI. Then in Travis, it checks out the UAT branch in every pod defined based on that environment JSON configuration I mentioned. Every image in the pod repository UAT branch is then updated to reflect the version that was mentioned in that JSON config for the requisite version of that pod. The changes to each pod's deployment YAML are then committed to the UAT branch of that repository. So it orchestrates those changes across all of the different repositories for each service. Each of these new commits trigger a build in UAT, in the UAT branch, the pod UAT branch in Travis CI. that then actually, again, goes through that same process, builds the container, makes all the appropriate configuration to change request, and pushes that through to Kubernetes. All right, so next, just to get you a little bit of a representation of what this looks like, I'm going to switch to this demo to sort of see basically what our source repositories look like. So as I mentioned, I'll start with the environment JSON configuration. So as I stated, we have an independent repository called environments. Within that, we have an environments JSON that has the appropriate configuration values for each pod in that environment. So we have a ton of different pods with a ton of different containers. Again, we're using this branch methodology, so we switch between dev, prod, QA, and UAT, and those all will have different configuration values based on the respective version that's being utilized in that environment. Similarly, the other point to represent, as I stated, we have separate repositories. So our source code in this case for the web application is all hosted in this single repository. And then we also have pod configurations, again, as represented in the independent repository. You'll notice, obviously, the source code is where all the devs are going to do their work. The pod is in this case, managed and monitored by a headless user that Travis CI uses. And as I stated, that will then update with the appropriate image as I represented in that earlier slide as well with the correct configuration value. Another key point to be aware of, all of these, as I stated, all of these tasks that I'm representing that are happening within the CI are all scripted out in our application. In this case, because we have so many services, they all share similar configurations in how the CI process works and how we plan on utilizing it. We have a common CI repository that forms the basis for all the scripts that we utilize across our application.